Welcome to this video on proposing reaction mechanisms from rate equations. It's the reverse of what we did before and by far the harder task. Now what we're going to do here is I'm going to just discuss briefly some features of plausible reaction mechanisms and then we're going to have several examples where you can practice proposing reaction mechanisms consistent with kinetic and other data. So some rules or tips. Now the two essential features of a useful, plausible, reasonable, correct, mark-worthy reaction mechanism are these. Number one, consistency with the rate equation. So the rate determining step, that's the slow step in the reaction, must have the correct stoichiometry as predicted by the rate equation. If you're not sure about that, go back to the last video to see what that means. Now, second is it's got to be consistent with the overall equation. And what that basically means is that if you make some intermediates in your mechanism, then they must be used up because otherwise they would be products of the reaction. Now those two things are essential. Now what's advisable is to keep to 1 to 2 molecules involved in each step. Trimolecular collisions are incredibly unlikely and any mechanism which proposes them is almost certainly incorrect. However, I have seen questions where trimolecular collisions have been allowed, so that's why I put it under advisable. Now the other thing I put under advisable is don't worry if you're making molecules that you've never seen before. The chemistry is likely to be unfamiliar in these situations because they're testing to see whether you can do the things I've put under essential. That said, things like having a fast step with involving nitrogen gas N2, it seems to be pretty fanciful, and if you're ever asked, for example, to show mechanisms involving protonation, then putting an H+ ion on a carbon is pretty unlikely. It's much more likely to go on oxygen or nitrogen. So you do have to apply some chemical knowledge to this, but don't worry if you're making molecules that you've never seen before or with unfamiliar formulae. Okay, that said, let's begin. So here we just have a reaction. Dinitrogen pentoxide is decomposing to make 4 NO2s and an O2 molecule. And the rate law that comes out of this is this one here, and we've been asked to propose a two-step mechanism for this reaction. Okay, so my first tip on this is to try to start with the slow step as being the first step. So if we put step number 1, step number 2, step number 1 as the slow step or the rate determining step, that would be my advice, and always make sure in answering these questions that you actually say which is the slow step. So that said, as we've only got an order of 1 here, then what we want is a single N2O5 molecule in this slow step. So N2O5 is going to be decomposing just by itself in the slow step. Now what's it going to make? Well, if you look at the products of the reaction now, well, the products are involving some NO2s. And if we think about how many NO2s we could make from that, well, we've got 2 nitrogens, so the maximum we could make would be 2 NO2s. Now what's going to be left from that? Oxygen. Now from your other chemistry knowledge you might remember that an oxygen atom by itself is actually a free radical. So it's going to be a very, very reactive species, and that would make sense. If this is a slow step that forms oxygen radicals, then oxygen radicals are subsequently going to react very quickly. So I've got my first step. I can see the stoichiometry here is consistent with the order in the rate equation, so I'm happy. That should get me 1 mark. Now what's going to happen in the next step? Well, we've only got 2 steps here, so the options are pretty limited. So let's look carefully about what needs to be in, well, let's start with the reactants. Well, in the overall equation I've got 2 molecules of N2O5 here. So I'd better have an N2O5 in my fast step. What else do I also need to make sure is in this step? Well, I've made an oxygen radical here. So I'd better make sure that I use that oxygen radical up, otherwise this mechanism would overall produce oxygen radicals, which the overall equation doesn't. So let's add an oxygen radical. That should account for all my reactants. What will that make as a product? Well, I've still got to make here, according to this, I've made 2 NO2s. I need to make 4 in total, and so I need to make another 2 NO2s. here. Now, does that actually make sense? Just as a final check, well, I've got two nitrogens, I've got 5 oxygens and an oxygen radical. Well, I've got 6 oxygens here and only 2 there. What I've done is I've missed out the fact that I've also got to make an O2, but that makes perfect sense because I've got 2 extra oxygens. So that as a fast step would seem to work. Now, I'm not saying that this is the reaction mechanism, I have no idea, but it is utterly consistent with the overall equation and the rate law. So and it's only got bimolecular or unimolecular events happening, so this should be pretty good. Okay, let's try a second example. Well, why don't you have a look at this one and see what you can come up with. Okay, let's see how you've done. Now I'm just going to, there are 2 options I could think of for this. Now yours may be correct, but not one of those. All that matters is consistency with the rate equation and the overall equation. So let's just think about what's happening here. So remember, first thing I would do is just to put the slow step first. And then we're going to have a fast second step. It's just the easiest thing to do, because then we can deal with our rate law. So 2 molecules involved, order 2 here means we've got to have 2 NO2s. So I better have 2 NO2 here. And that's all I can have. Now what could that go on to form? Well, let's have a look in the products and see if it could reasonably form anything in the products. Well, I think the obvious one that it could reasonably form is NO. So we just need to make 1 NO here. So there's no point in making more than 1, because then we just have to use up a product, and that doesn't make too much sense. So let's have our product molecule NO formed here. So what does that leave us with? Well, if we count up our atoms, we've got to have an NO3. And this is going to be a reactive intermediate because it's not a product. So immediately I'll pop that into my fast step because I know I've got to get rid of it. And then I think about what other reactants have I missed? Well, other reactant I missed is carbon monoxide. So I better put carbon monoxide in. And what's that going to make? Well, I've got to make a CO2. So I'll put a CO2 in. And what else is missing? Well, the other thing if I count up my atoms, I've got a nitrogen here, and I've got 2 oxygens left. So I better make an NO2. And it's a good job I'm doing that, really, because I've only got 1 NO2 at the start here, and I've used 2 here. So if I add up these steps, I should see that actually, so if I sum the steps, this should work. So NO2 is going to cancel with 1 there, so I'm going to get NO2. The NO3s will cancel, and I get carbon monoxide, an NO, and a CO2. So this mechanism should work. Apparently this is the correct one. Now here's another one that you might have thought about. NO2, you've got to have 2 NO2s in the first slow step. So slow step number 1, 2 NO2s again, because of the rate law. And instead of having the NO, you could have just dimerized this and formed N2O4. That's a perfectly valid reaction. So where does that leave us then? In our fast step, we've got a second step. Well, the intermediate's got to be involved. We know the carbon monoxide's got to be involved. What else? So now we've got to make sure that we produce an NO2, because we need to make sure that cancels with 1 of those there. We better produce the NO that we need overall. And we better produce the CO2 as well. Does that all fit? So 2 nitrogens, 5 oxygens, yes, a carbon. Yep, that looks good as well. So that's potentially correct as well. Apparently the left-hand one is better, but that's perfectly mark-worthy. Okay, things are getting a bit harder. Try and pause the video and see what you could do with this one. Okay, so immediate alarm bells should be ringing in your mind, because the overall order of this reaction, overall order, is 2 plus 1 for the chlorine, which is 3. So if we put the slow step first in this reaction, then we're going to end up with a horrible trimolecular event, which is just never a good idea. So let's see, take our first step here, and we're actually going to say this is a fast step. So that means our slow step is number 2. Okay, so now we're never going to get these reactants all coming together at once, but remember what we said in the last video about intermediates being involved. If we can have an intermediate being formed which reacts in this slow step, then we can essentially replace the concentrations of the reactants of the intermediate with the product of the concentrations of the reactants that formed it in preceding fast steps. So let's say that we have an intermediate that's going to form. I'm just going to call it I for now. And because I like bimolecular events, I'm going to have that just reacting with a chlorine, because it makes most sense to me. So the intermediate is going to react with a chlorine, and that's going to make my products. Because I want in my fast step the intermediate that's going to form. And feel free just to use the letter I if you don't know what the intermediate is likely to be. And then this is going to form my products, 2NO-Cl. So what could the intermediate actually be? Well, if the chlorine is included here in the slow step, then in the fast step preceding it, you've got to have NO plus NO, because they appear up here. There's 2 NOs, so I've got to have them coming in there. Chlorine from here, coming in here. And so that intermediate, and obviously if you're just going to make one intermediate, it's just to dimerize. So we can have as N2O2, and N2O2 then appears here. So that's my intermediate. Now let's just quickly check that this is actually consistent. 2 NOs, a Cl2, the intermediates cancel, 2 NoCl. So it's consistent with the overall equation, and because this is the fast step, essentially this is the slow step, would be concentration of that, which you'd replace with NO squared.